Thank you. So this talk is probably going to be a bit different than the rest of the talks at this conference because it's not so much about monitoring but the scaling of the whole system, but I will go into what we use for monitoring and how it helped us to get to this scale. So my name is Josip. I'm the CTO at a company called SofaScore. Can I get a raise of hands on how many of you know what SofaScore is? Okay, a couple of people. So basically it's a sports platform that allows you to follow live results statistics for more than 20 different sports. It's free and we have a lot of users. So this is how the app looks. I put the screenshots just to see that we do have a lot of data. It's all sports data. We do heat maps, we do statistics, we calculate a lot of different stuff, but the app itself is not really important for this talk. These are the monthly stats. So we have more than 28 million monthly active users, which generate more than 1.4 petabytes of traffic each month. That's 400 billion requests. I mean, more than 400 billion requests. And the peak was 1.6 million requests per second. So it's not a small system. I mean, it's not Facebook large or Google large, but we have some interesting challenges. So long time ago, when we started, we had zero monitoring and zero observability. So it was just one server, and then people would come online. And the thing is, so people usually come online when there's a game being played. So we have periods of basically no traffic and then a lot of traffic. And if you don't have observability, the server will just die. And we did not know why. So that was a problem. But you know, in computer science, everybody tells you just put cache on it, it will work. So that's what we did. We put memcache. And it was a full page cache. So basically when users would come, if it's not in the cache, it would be calculated, saved to the cache, so next user would actually fetch from the cache and it would be faster. But the problem with this is if you do this, at a certain point in time, you're gonna run into something called cache stampede problem, which is when something is not in the cache and you have a lot of users, which we do, so they all come basically at the same time. All of those requests, the same requests will get calculated over and over again, and basically your database will die, or your backend servers, or whatever. What you want to have instead is to allow just one request of all of those same requests, allow just one request to go to the database or to your backend servers, calculate that, and then return that to all of the users. But this is difficult to do, especially on the application layer, because you have to queue all of the requests, and most of the apps don't really allow you to do that. So instead, what we ended up doing is we were thinking on, so probably most of the users want to open the games that are current now, right? So what we did is we created a worker to proactively look at all the games that are being played right now, or plus minus 2 hours, and then put that in the cache before it actually expires from the cache. And this is a really cool mechanism that all of the companies that have a larger scale are doing. So if you open your Instagram or whatever, they don't calculate that in real time. It's calculated before and it's saved for you. So when you open it, it's instant. So it's really important to know how your users are interacting with your app, with your system, to be able to better optimize the system. And now, at that point in time, we did know something really well. We knew the number of users that are on the site, and we knew the load of the server. And basically, that's all that we knew. So 15 minutes before the game, we will have a certain number of users. And in those 15 minutes, so just in those 15 minutes, the number of users will triple or even quadruple if it's a big enough game. So we have a certain load, and then in 15 minutes, it's 3 or 4 times more. And a big game was being played. So for all of you who don't follow football, there's this thing a global event. It's called El Clásico. That's when the two most popular football teams play each other. It's Real Madrid and Barcelona. And it is the most important event for us because you have the most users, the most money, everything is at its highest. So 15 minutes before, the server had its CPU through the roof. And we were not on the cloud. So this was like 10 years ago. And we cannot scale. So we have 15 minutes before everything will break. And nobody will get to see the results. And we will lose a lot of money. So we are thinking, okay, what can we actually do in those 15 minutes? There's not a whole lot you can do if you're not on the cloud. So we got to thinking and we realized we were running PHP on the backend. We were running PHP at that point in time. So we knew that the web server itself is really fast compared to PHP because even if you have cache, your app still needs to load the whole framework, read from the cache, return to the user. It's not really fast. So we were asking ourselves, what if this was actually a static content? So because all of the users, so all of them that come, basically come to just one page, to El Clásico page. So it would be really great if that was just static content. And then we were like, well, it can be, right? So you just go on File, Save As, because it's a web page. You save the HTML, and then we wrote a rule that said, on htaccess rule, right? If user comes to El Clásico, return the file. So we did that, and users were getting static files, which is super fast. The load dropped. Everything worked. So we saved the day. But the issue is, as you probably know, it's static content. So it doesn't change, which doesn't mean a lot if you have a live score site to see the live results, and you don't see the live results, that's a problem. So we were watching the game on the TV. And when the goal happened, we would edit the HTML file, save it, upload it to FTP, and then everything would work, right? So that's how you scale. Thank you very much. See you later. But yeah, so that worked. But the thing is, this was the turning point where I got to the founders and I told them, like, this will not work for us. So we cannot keep doing this every time. We need to try out new technologies. And the cloud, when you think about it, is the perfect use case for this. So most of the time we have really low usage. And then we need to scale 5 times. And then after 3 or 4 hours, we need to downscale back to the baseline. And they said, sure, okay, do you know how to do it? And I was like, sure. I mean, how hard can it be, right? You just Google it. I was in college at the time, so I was full of energy. I believed that we can do anything. And AWS was the obvious choice because it was the only game in town back then. And looking back at the story I told you, I wanted to have a system that will basically emulate the speed of the static server while also maintaining the dynamic content. And I found this. This is what we use today. It's called Varnish. It's basically a reverse HTTP proxy that respects the headers and is super, super fast. Will cache your content, and then once the TTL is done, it will refresh the content. And it has request coalescing built in, which means if something is no longer in the cache and you get millions of users and they all go to the same content, only one request will go to the backend, and then all of the users will get the same content. It will get cached. So that's what basically keeps your backend services protected, because only one request at a time for one content will ever reach the backend, which is super, super cool. So when moving to the cloud, what we did is pretty straightforward. So we built an Amazon machine image, which had all of the software baked in. It was in an auto-scaling group, and we could do this pretty easily because there was no state on the app itself, because everything else was in a database or on a separate server where files are kept. And we had workers. We could get rid of Memcache because we had Varnish. So the important thing to have is when you're building a system from early on, you should be stateless wherever possible, because scaling state, scaling databases, it's really, really hard. And especially if you have files in your machines, that never works. We were also trying out new technologies, and we found out about Mongo and decided to give it a go because, you know, web scale. It worked fine for a time, and then it didn't because we had replication issues, which are really hard to catch. We had data type errors because long integer is not the same as an integer in MongoDB, so when you query, you don't actually get the data that you want to get, which is super funny. It's difficult to analyze data, again, because it's a NoSQL database, and what we do is we analyze data, so this was not a great choice for us. It had issues with locking because at that time, the locking was on the collection level, and we do a lot of updates, so most of the time it would just get locked up, didn't work, and you had no foreign keys. So we could not have the consistency in our data. And we figured out that we made a mistake, and we want to roll back. So we started looking at SQL solutions, and now everybody will tell you you cannot build a big system and have a relational database. That's not true. So we are running Postgres. Why Postgres? Well, it's open source, which is really important to us because it's flexible and it's free. It has advanced SQL capabilities. It has minimal locking. It has this technology called MVCC, multi-version concurrency control. It can be a whole talk on itself, but basically what it does is you can update and read at the same time, which is important to us because we have a lot of updates and we have a lot of users who read a lot of stuff. The performance is great. How great? So we get 1 million queries per second, and we can do 90,000 transactions per second in a benchmark. And one transaction is actually 5 things that change the state. So basically 500,000 updates and 1 million reads per second. So we decided we were going to switch to Postgres at that point in time. But the problem is the app is global. So the users are worldwide. It's always something being played in sports, so you cannot shut down and do migrations and updates. So in my mind, it looks something like this. So you're driving on a highway, like 90 miles an hour, and you want to change the wheels. And again, we were young, we were crazy, and like, sure, we're gonna do it. How hard can it be, right? So what we did is we timestamped all of the data, all of the collections in MongoDB, and then did a tool that would normalize the data and copy to Postgres, and then on each run, it would just do less and less data because it would look at the timestamps, and it worked. Once we got everything to Postgres, we would just have one machine as a canary to see that it works. If it worked, then we just deployed everything, and it went pretty smoothly, which now that I look at it, I find really hard to believe, but it worked. So the pros and cons of this is that we lost the simplicity of Mongo because Mongo is really simple to set up and run, but we gained stability and could actually do analytical work that we need to. And that's what we are running today. So we have a master and a replica setup. It's really high performant, and it basically serves all of the users without any issues. So I think it's really important to recognize the right tool for the job and change if necessary. If you're using technology that doesn't really fit your use case, you should change, because the longer you have the technology that doesn't work, you're going to have a bigger and bigger problem. And Postgres has some really cool things built into it. So it has PG stat statements that aggregates all of your queries since the last time you reset it, and you can see which queries use up the most time, which are most time consuming. So you know how to optimize your system and see what's causing you issues. And there's a cool tool called PG Hero that allows you to view that visually. That's what we are using. We also log all of the statements that change the state of data. So inserts, deletes, and updates. We log everything to Elastic so that we can debug, and we save this for a month. So we are running the Elk stack for logging and for logging of the queries. We also have Monolog to log all of the statements, and it has this really cool feature that's called fingers crossed logging. If you haven't heard of it, it basically means don't log anything, keep it in memory till the end of the request, but if an exception happens, then push everything to the log. So you get debug statements just for the things that are causing you problems. And we have around 1 million records every hour in the cluster, and it's not a big cluster, it's just two machines running in high availability. The rest of the stack is Influx with Telegraph and a statsd plugin. I really love the statsd plugin because it's super simple and fast, and you can basically write it in any language. You just put your metric and then counter, and that's it. So we visualize everything with Grafana. We also use Grafana for alerts and dashboards and some other stuff that I'm going to talk about later. But this is the stack that we have. It's working pretty great for the users that we have. So the cloud was a fairly simple setup. We had everything on one image. But the problem with this is even though Varnish has request coalescing, so it only allows one thing to go to the backend, once you scale and when you get more machines, you will have a cache that no longer is as good as it can be, because the more machines you have, the more requests will actually pass through the cache, because every cache is on its own machine, so that's not really efficient. To solve this, it's not really rocket science, so you basically just separate your caching layer in front, and this works well. But the thing is, I really like optimizing stuff, and you can see here that if you have two machines, you will have two requests because they're separate. I want to have just one request for one content at a certain point in time. So to solve this, you can do sharding based on URL. So every machine, depending on which URL is fetched, will go to a different caching server. It has consistent hashing built in. So even if one machine goes offline, you can the data will not get scrambled altogether. So the way we are using this actually is to have two layers of varnishes. One is to load balance and have a lot of CPU, and the other is just to increase the memory capacity of varnishes. And basically this allows you to cache everything, and we do. So we cache a lot of data, but the thing is, cache and validation is really hard. This is running joke in computer science. Two of the hardest things in computer science, so two hardest things, is cache and validation, naming things, and off by one errors, right? So invalidation is really hard. But if you manage to do it, the benefits are really high. So we get, so this graph doesn't look all that impressive, but like you have this line up there, which is the hit rate, which is close to 100 for us. So most of the things, most of the requests are actually served from the cache. And we do this by building out a graph, all of the dependencies, and it's actually an open source library, so anybody could use it. We know if something changes, which endpoints we need to invalidate. So for example, match details that can change second by second, we actually cache those for 2 days. But if a change happens, we will invalidate, so a new version will be available. And that's what allows us to keep the high hit rate. So AWS, working great, amazing. But the thing with cloud is, all of you that use the cloud know that it's really expensive, especially the traffic. So traffic is absurdly expensive. We got to a point where we were paying more for traffic on AWS than for everything else. So compute was nothing compared to traffic because we have so many users and the cache is really great. So I got to thinking, maybe if we were to separate the cache layer that we have, since it is separate, we just move it away from the cloud and then keep everything else in the cloud. So that's what we did. We moved the caching layer off the cloud and to on-prem servers, not in our office, but we rented out a server. You can rent servers out bare metal for a month. And they usually have either really cheap traffic or basically free. And it's quality traffic, so it's not like you get bad uplinks. So we did that, and it was pretty simple to do. You just change the DNS to point to the different IPs. And since a lot of it is in the cache, only a small percentage would go to the cloud. So we got a 10x reduction in our cloud bill. for traffic, which is a lot. And then when I saw that everything is working great, we were thinking, well, if this is working great and it's really cost effective, what if we migrated everything off the cloud? So that was a point in time when everybody was coming on the cloud. We were like, okay, maybe it's time to move back to how it was before. And the reason why I felt confident that we can do this is because so we have a lot of users and really big peaks, but the thing is most of the peaks are cached, and this is a graph of requests that actually go to the backend service, so the miss requests, and it oscillates from 100 to 200. So not a lot, just basically by a double. So we could over-provision the system by a double and know that it will not get out of capacity. And that's what we did. So when we rented out the servers, we rented out twice as much as we might ever need, and we still got a 4 or 5x reduction in price. So we were paying 20% of the bill to get the system that can handle double the scale that we ever had. And we migrated everything to on-prem, basically used Docker and a couple of other tools to do so. We weren't as coupled to AWS, so it wasn't really hard. We had to do our own database, but again, Postgres we weren't actually using RDS from AWS. We were running Postgres our own, so it was pretty straightforward. We did that, and this is the cost throughout time. So when you see the red stuff, that's when we moved away from the cloud, and then it got a little lower, and this might not seem impressive, since it's like, okay, you see, we flatten it out, and it's not so much. But if you overlay that with the growth of the users, which is the green stuff, you can see that the users grew almost exponentially, and the cost kept getting lower. So we got more and more efficient with running on-prem, and it wasn't related to the increase in users. And the other thing is, I mean, it's at the same time, it's good and bad. So if you have a bug in your code, on the cloud, it will work, you will pay. So if you don't use your resources correctly, everything will work, everything will scale, you will pay for that. On-prem, if it doesn't work, you're offline. You have to fix it. But then again, you cannot get a bill. So this is a true screenshot from a friend of mine, will not name companies, but their bill was $360K, and one of the developers pushed out a bug. So they got to 1.6 million. I think this was in 1 day or 2 days, I don't know. So, you know, it's win some, lose some. And on-prem, we have a lot of spare RAM because PHP is really efficient with memory, so we have a lot of RAM. So what we do is we have varnishes on all of those machines with the sharded cache. So we have a lot of memory for cache, and everything is in the cache. Nothing gets evicted. And usually I get a question, so okay, you are saving money on cloud cost, but what about people? You know, people cost too, and you have to have more people. The thing is, up until 3.5 years ago, I was the only one doing everything, part-time. So, you know, it's possible to do it. Now we have a team, a DevOps team of 4 people, and they do that part-time as well. They are backend developers who do couple of weeks every quarter. They do DevOps stuff. So if you build out the system and you don't complicate it as much, it doesn't really cost. And on the cloud, you also have to have people, and they have to know cloud stuff. So basically, not much difference there. This is a screenshot from the number of requests in time. And in football, you have 2 halves. First half and a second half. So you can see the spikes really well. And the thing is, this looks like a DDoS attack, right? So you have small traffic, and then you get really high up. And we had an issue where Cloudflare, which we use as our CDN and DDoS protection, they were detecting this as a DDoS attack, and they were blocking our users. Because we send out a lot of push notifications really, really fast, and users who follow sports are really fanatical about their team, so they open it up immediately and click. So you have millions of people clicking at the same time, and that's a DDoS. So I have to actually go to their offices in San Francisco to talk with their engineers, and I explained that, we have this issue. I'm not able to get your support to really understand what's happening. This is our use case. This is what happens. And he was like, oh, yeah. I mean, this is like a DDoS. You're definitely tripping the system. This is blocking our users. And I was like, can you do something about it? Sure. And he he just wrote, if Sofa scored, then don't do this. And I think that's still in their system, so that was funny. Since this is an observability and monitoring conference, I think it's really important to do that from early on. So before we were using New Relic to do application performance monitoring, and I really love this kind of approach because you have the most time-consuming stuff, so you can really focus on optimizing things that make sense, because you don't need to optimize something that's called once a day, right? But if something is called millions of times a day, 5 milliseconds optimization can mean a lot. But New Relic is really expensive, especially on the number of requests that we get. And we don't need all of that fancy stuff with all of the complicated graphs. What I need is this. So I need the most time-consuming stuff. I want to see which endpoints get the most calls and which are the slowest, and then also in aggregate, which consume the most time. So we built this out ourselves, and it's not really difficult. So on end of every request, you just put something to influx. You say this endpoint the duration was this number of milliseconds, and it does everything else. So you can get the most time consuming, the most requests, whatever you want to do. And we also implemented ourselves, again, on the same simple way. Every time a query to the database is, queried, we log which controller did which query and how long it lasted. And then you get really cool stuff where you can see which controllers do the most queries, and also which queries last the most time. Then you can see stuff like this where something is a real outlier, and then you go and optimize that, because if you use an ORM, you can get queries that load in the background a lot. So it's really easy to optimize with this kind of thing. And it was just a 10-minute work of one of the developers just to write a listener and to send out a metric. And then we can see a breakdown of all of the operations based on read and write. And you can use this, since we can store it for as long as we want. This is a graph of two endpoints that are closely related, but at a certain point in time, they got to be the same, which was weird. And then I got to the platform team and I said, okay, this looks weird. They looked at the code and said, oh yeah, we are calling the things that we're not supposed to be calling. And then they fixed it, and then it went back to the way it was. So you can do, if you have good observability and monitoring, you can do optimizations, which is really important, because if something is called a lot of times, then you should optimize and get it to the better state, and then you don't need as many resources. But also sometimes you cannot optimize, so it's already the most optimal version. Usually, what you can then do is increase the cache. And what people usually don't realize is increasing the cache just a little bit can have a really big impact. So it's not a linear connection. So if you increase the cache by a double, you might get 10x reduction in number of calls. So it's really important to do this correctly. And usually people say, yeah, but our system, we have personalization for the users. We cannot really cache. Yes, you can. You can always cache. So we have personalization in our app. We can cache that. You just have to do some stuff differently, but it is possible. If you want to know more about that, it's a bit more complicated, but you can catch me later. We can talk about that. And I really love the quote from Donald, which says, like, premature optimization is the root of all evil. I completely agree with that. But then again, like there are those 3% that you really need to focus on so that your system doesn't escalate. So monitor everything, optimize something. I also get a question. Um, what if the number of users exceeds your current capacity, considering you're not on the cloud? So we cannot scale because we have to rent out machines by month or by year. So what we do is with the provider where we rent out the servers, they also have virtual machines. So we have dedicated machines, and then if the load gets high, we just spin up virtual machines. They join the cluster. The load is distributed, and everything works. So it's kind of a hybrid cloud approach, and the way we solve this is also pretty simple. So we have Influx and Grafana to monitor a lot of stuff, but we focus on queue time. So the time it took from Varnish to receive the request until it was actually started to be processed on the backend. And we just did a rule in Grafana Alert to call a webhook, and that webhook just spin up new machines. That's it. Pretty simple. Again, like 10-minute work to create the alert, and the webhook is just an API call to the provider to spin up machines and have a script that initializes the VM and joins the cluster. So the load drops. And now our servers are in France, and to the rest of the world who's further away from France, unfortunately, there's speed of light. So speed of light is not, I mean, it is fast, but if you're further away from Europe, you can kind of get to see that. So I've sent out an email to one of our users who's in Australia, and I asked him, can you please record you using the app so that I can see what your experience looks like? Because in Europe, everything is fast. And he has said, sure, mate, here's the video. Everything is fast. Everything is working great. And then I opened the video, and I saw this and this. Honestly, I didn't know we had loaders implemented, which is good. Like, we have loaders. That's great. It's a user experience. But in Europe, you don't get to see this because of how fast it is. Since in Europe, everything is cached. You get it to you're closer to a user. Everything works. And then, okay, so we need to solve for this because there's a great opportunity there. So since we have the caching layer, we just split it out across the world instead of having it in one place. And it's really easy to do compared to like multi-master application and stuff like that, which is hard. So this is just split out the machines, and if it's in the cache, they will give it to the user. If it's not, they will load it and save it. And the thing is, we got a reduction in latency from half a second to 80 milliseconds for Australia, which is a lot. So you go from, oh, I can see a loader for half a second to like 80 milliseconds is almost imperceivable. So we got a really big increase in number of users there because like nobody cares about those. Like for apps to be slow, that's normal for them because they're used to it. So if you do something that's faster, they will love it. And now a CDN should do that, but the thing is CDNs have a lot of different clients. They evict stuff from the cache. Usually they have really low number of purges you can do, so that's a problem. By doing this ourselves, we got to a point where it's really, really fast and it's local for every user. Also, data centers can burn. This is the provider that we are using. Fortunately, this wasn't the DC we were in. But you know, cloud is also a physical machine, so that can burn as well. So you should always be in multiple regions, and doing that kind of gets complicated. So we switched to Kubernetes. We have three data centers, but we are using Kubernetes because it's data center aware. So you can do routing and do things efficiently, and all of the cool things that you get with Kubernetes. We're also using Prometheus for monitoring and alerting, which is really great. But the thing is, like, if you're not using Kubernetes and you're thinking about using it, think twice. It's really hard to do correctly. I mean, it's really easy to set up. Like, you set it up, the POC works. And then when something breaks, if you're not really into the system, it's really hard to fix. We crashed the cluster like 4 or 5 times in production the first year. So that was really fun learning experience. Now the guys know how to do it, but like it's really difficult. If you're on the cloud, you have a lot of cloud primitives. You probably don't need Kubernetes, but there are cool stuff you can do with it. We are also using Longhorn since we are on-prem. You don't have like elastic block storage or any kind of distributed storage. This is it. So this is Kubernetes native. You can have your storage distributed across different data centers and replicated. I actually saw people using it in Kubernetes deployments on the cloud because you can have multi-AZ or multi-DC replication. So if the whole zone gets down, you can spin up the same instance with the same data in a different data center, which is cool. But again, increased complexity. If you're on the cloud, I wouldn't recommend it. But for us, this solves the state problem in Kubernetes. We also have a lot of data. So every click that the user does is we use Firebase to monitor that. And everything is sent to Firebase, and then we download it because we don't want it to be there because it's expensive. So we download it and keep it in our machines. But the thing is, you have to save 2 petabytes, which is difficult if you're not on the cloud. If you're on the cloud, you just BigQuery or whatever. But off the cloud, it's hard. So what we do is we use ClickHouse. ClickHouse is, again, an open source tool, which is great for analytical workloads. It supports SQL, so you can do SQL discovery. And we use Apache Superset, also open source, to actually visualize all of that. And we get crazy performance with that. Both software is really cool. So we saved those 2 petabytes, and on disk is actually 46 terabytes. So the compression ratio is crazy. We have 1.4 trillion rows in ClickHouse, and the insert can get to more than 2 million rows per second when ingesting. So it can handle a lot. And then you can do cool stuff like analyze all of the HTTP logs that we have and figure out which IPs are going through the cache, which means that they're scraping, and how many different user agents they have and number of requests, and analyze all of that and figure out which IPs are scraping and then block those. It can basically analyze hundreds of millions of rows in a second. So really crazy numbers. And this is how it looks like, so you can really track what the users are doing. We also do real-time updates. And to do this, we're using NATS, which is basically a pub sub server. So the apps will fetch via REST, and then they will subscribe to a topic. So when a goal happens, they will just receive it immediately on the topic. And it can also ingest data. So we are actually using this to get rid of the Firebase and do everything ourselves based on open source technology. So you can basically do monitoring of the users in the app anonymously with this. And we send out, so this was the number of connections that we had in peak was 835K on just a couple of machines. It's really performant written in Go, and we do 500K messages per second outbound to the users. And all of this combined, when you do that, our infrastructure cost is 0.6% of the revenue. So everything that we so we use a little bit of the cloud, all of that, all of the CDNs, all of the machines, everything that's needed to run is just 0.6% of the revenue. So to finish up, cache all the things, that's the most important thing. The second most important thing is to monitor everything, optimize something, know how your users interact with the app, be stateless wherever possible, recognize the right tool for the job, and change if necessary. Cloud should be the default, but you should keep your options open. I see a lot of companies actually thinking about moving away if they have a big enough volume. And try to keep it simple for as long as you can. Because once you get to complicated stuff, it's really difficult then to scale. And thank you. That's it. I don't know if you have time for questions. We have time for questions.
Thank you, Josip, for showing us your process of scaling your infrastructure and fixing all the issues you came across. So if there are any questions, please feel free to ask them right now.
Hi, thank you for the presentation. It was very great. You talked a lot about the data the users are collecting. What about the data or the statistics you have to collect for the games? Do you monitor them? Do you have multiple resources or sources for the data you're collecting?
So we have I think more than 30 different sources of data. So we buy everything that we can buy, and then we scrape everything else that we cannot buy, and then everything that's unscrapable, we have a team of people that will actually manually do that. And all of that gets combined and deduplicated and then put into a single thing that you see. And we monitor all of those pipelines. We monitor all of the jobs, all of the things that get parsed. We monitor how long it takes, how many things have changed, how many jobs there were there any anomalies in there. So like we monitor everything.
Okay, nice. Thank you.
I think there was another question somewhere.
Hi, thanks for the talk. Really, really awesome story. So I have two questions. One is regarding your varnish infrastructure. So we used it a lot back in the days for an e-commerce shop where we basically sold the first COVID tests online over here in Germany, and it was running on 2 VMs, so it scaled as hell. So, but I would be interested in how exactly are you doing the cache invalidation over all the nodes you have deployed? Because basically you rebuild fastly somehow because they're using the same technology, but how are you doing this shared cache thing and then invalidate all the nodes over the globe?
Yeah, so what we do is we're actually using Fastly right now. So the global system that I showed is no longer what we use. We just use Fastly for that, but we still have 2 layers on our own because even though Fastly is great and can do invalidation on a high level, you're one of the customers, so you don't get the efficiency that you can if you also have varnish on your end. So it's always cool to have your own. What we do is we invalidate from the lowest layer up, and then we invalidate the first one in parallel. When that's done, we invalidate the second, and then we do a call to Fastly.
Okay, I understand. So, and the second question would be, I really love your cloud exit story as well. I hope to read it somewhere. Is there a blog post on it?
There is, like yesterday, there was a podcast, a snippet from a podcast that was on my LinkedIn, so you can probably find that.
Okay, and I've seen the link, but I was wondering about the story. And the last question is about the data. So you didn't mention AI once in your talk, but kudos for that one. But I'm asking it because you have so much data on soccer games. Will you in the future write news articles based on all the data, because you can write a pre-game article and compare the games, yellow cards, I don't know who played and stuff like that. Is this something on your roadmap? I have to ask this because we share a customer and he was interested in if you're doing that.
Yeah, we are actually working on that.
Okay.
To have that. We actually have AI to predict which game is going to win. So you can make money off of that, but it's closed, so I'm joking. You should not bet, you will lose every time. We do have AI in terms of, so we have a lot of user actions. So we know, we use machine learning to know which users are likely to continue being good users and be even power users. So we use that to calculate in the first week what's the probability that they will stay long-term, and then we feed that signal back into our campaigns so that we can tell to the campaign, give me more users like this, and then we can optimize those campaigns to get users that are more relevant for the same amount of money. So that's where we use AI, but sports analytics is something that we weren't doing AI with yet, but we are starting to explore that. So we have SofaScore player rating, which is just a float that tells you how good a player is, but that's not AI. This is just an algorithm that uses, because you cannot use AI there because then it's not, you cannot know why you got the score that you got. So we use 120 different statistics to calculate that one score, and it's objective and it's the same across the board. We actually know that like players are looking at when they when the halftime is, they go to their lockers and then they see the score. But it's not AI.
Okay, thanks. Next one.
I think we don't want to cut off your break, or if you don't care, you can stay and we can ask some more questions.
I hope this works. Good throw.
Basketball.
Touchdown. You showed us how you used to scale up the whole system with Grafana. You just do a webhook or something like that.
Yeah,
what is the call for the scale down again? So how you revert this?
Yeah, so,
manually?
It's really dumb way, but it works. So basically, when the machine is spun up, it will shut down in 4 hours. That's it. That's it. Because like we actually don't get to scale up a lot. It basically almost never happens. When it does, it's usually Saturday at 2 p.m. because that's when most of the games start to come. And then all of the games that do a lot of traffic are done within 2 or 3 hours. That's why 4. So, but I mean, you can do that in Grafana as well. If you see your load that is too low, then you can just do a webhook that will scale down again. But we didn't want to do that because like we know how the system will behave, and there is no need to downscale. And if you downscale incorrectly, then you will have an impact on your system, and then you don't maybe want to do that. But yeah, that's a good question.
All right.
Okay.
Thank you, Josip.